Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, well, I'm just going to remind you the 3 books that are on sale. Drink tea and read the paper. If you're a green belt and a black belt and you want simple instruction on how to apply your skill, design of experiments for 21st century engineers, and finally, a statistical process control for small batch production. They are all available from lulu.com and the links are in the video below. Welcome to the latest video, and in this video newsletter, well, what we're going to talk about is the manual analysis of a DOE. So I'm going to show you where the factorial plots come from, or the marginal means plots. Depends which piece of software you use. Sometimes they're called factorial plots, sometimes marginal means plots. So we're going to show you manual DOE analysis, and essentially the factorial plots, the marginal means plots. Now this comes from a question from a viewer on YouTube itself. I posted a particular case study where I showed you a welding DOE, and I'll put the link to this case study in the video below, so you can go and take a look. But here is the data set that we created. So you can see that we're running a Taguchi L12. So here is the L12 with the results at the end for the weld quality, and following this data set on the next slide, I'm showing you the factorial plots. So you can see, look, there are 2 variables that are identified as being very important. It's the first variable and the 4th variable in the DOE table. And the question that I was sent was, okay, how did you analyze that? Where did those graphs come from? Where did the marginal means graph comes from? So let me show you how a DOE is set up and then how the graphs are created. So in the first column of the DOE, and this was a Taguchi L12, and certainly in the software that I use DOE Pro. Whenever I set a DOE up, the first column is always like this. It is split 50-50 for low values, which are indicated by the -1, for high values, which are indicated by the +1. Now, of course, what you're going to do is you're going to substitute those values for real numbers. So let's say we were trying to understand what time does to the process, and we substituted 5 as the low value, ten as the high value. All right, so we're doing 8 experiments, and for variable A, which is time, we're going to test 5 and 10. It's a 2-level experiment. We're testing in 2 places. Okay. So obviously there's more of an experiment, like the Taguchi that you see here. In this case, I think there's 9 columns of variables that we're analysing. So obviously there's more of a test here. But when we come to do the analysis, we're going to do an analysis for variable A, an analysis for variable B, C, D, E, etc. And they'll all have a different marginal means value, marginal means graph for what they did to the process. So assume the rest of the tables here, but of course what we've then got is results. So let's say we get 5, 6, 5, 6 for these results, and then we get 7, 8, 9, we'll go 7, 8, 9, 10, okay, for those results. So that's the result set that we've got. This result set will be used for every analysis. Now that's the power of DOE. So we'll use all 8 data points to find out what A is doing, but then we'll use all 8 data points again to find out what B is doing. Then we use all 8 data points again to find out what C is doing. Each time we do the analysis though, we use a different combination of these 8 results to get the answer. Now the easiest one to show you, of course, is the first column because it's just split 50-50. We do a very simple thing. We just say, look, the top 4 rows were all set low. Work out the average. In this case, the average of those 4 is 5.5. Take the bottom set of results, work out the average. So I think the average is 8.5. I'm going to guess the average is 8.5. I'm not working it out. So if anybody's watching and that's not the average, please don't send any comments. So we got 5.5 as an average when we were set at 5. We got 8.5 when we were set at 10. So let's plot the factorial plot. So we did tests at 5. We did tests at 10. Let's do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Like this. So we had a result at 5.5. We had a result at 8.5. And we join the dots. And there is your factorial plot. This is what time is doing to the process. So time has a delta. It is shifting the result by 3 units, and that's represented by the graph. Now if we go to the data that we've got on the video that the question was about, if I look at the second column, which is actually the tip condition. So one of the things we tested in this DOE was the age of the tip on the welder, because obviously you have to replace these, and everybody wonders, I wonder what happens if we have an old tip compared to a new tip. Does that affect the welding quality? So that was one of the things that we tested. So -1 in this case represented an old tip, +1 represents a new tip. Now you can see in the pattern, one of the reasons why I'm picking this second column is because I can actually show you where the data sits, because the second column, look, was split into 4 groups. There's 3 low values represented by -1. Then there's 3 high values represented by +1. Then 3 low values again, then 3 high values again. So if I show you where the data sits now in the data table, so if I highlight the low value results in the green, so you can see, look, this block of 6 results and this block of 6 results will get averaged. They're in the green. Then this block of 6 results and this block of 6 results will be averaged. They're in the red. So if I now go to the marginal means plot, the factorial plot, this end of the graph was the average of those green results. This end of the graph was the average of those red results. And that is how the marginal means plots gets created. So each time you take the results from your DOE and you cut them in half. You work out the average of one half against the average of another half. But each time the halves are different. So for instance, if I put factor B alongside this one, look, factor B would be split like this. So instead of doing the top half versus the bottom half, now what we do is we'd average those 4, plot the average, put it on a graph, against those 4, plot the average, put them on the graph, draw the line. But each time it's 50% of the data versus 50% of the data, but each time that 50% is cut in a different pattern every single time we do this. But that's the power of a DOE. You can see on this DOE here, I have 12 results repeated twice. So I have 24 data points. The 24 data points have been used to analyze 9 variables. It's the most powerful, it's the fastest way to find this information out, because for only 24 data points I get 9 answers. I don't have to do a test on its own for factor 1, a test on its own for factor 2, etc. I just do a test, and then all 9 pieces of knowledge are generated on those 9 marginal means plots that you see on this diagram here. All of that knowledge comes from just cutting the 24 data points up in different combinations. So that is how a marginal means plot, a factorial plot, gets created in Minitab or DOE Pro or any other DOE software that you use. Hope that has clarified the point and answered the question. But hey guys, DOE, if you're an engineer and you don't use this, you're missing a trick. Design of experiments is the fastest way to find out the most knowledge about your process. Use it and make bucket loads of cash.